So in this example, we're going to find a pair of solutions to the differential equation y double prime plus 5y prime minus 6y equals 0. So what we start out with is we let y equals e to the power rt, and we plug that into our differential equation. And so if y equals e to the power rt, we've seen before that y prime is r, e, r to the power t, and then y double prime is r squared, e to the power rt. So let's plug that in. Y double prime gives us r squared e to the power rt, and then plus 5 times y prime, that's r e to the power rt, and then minus 6y, that gives us minus 6e to the power rt equals 0. And then we can factor out an e to the power rt, and we get r squared plus 5r minus 6 equals 0. And so our auxiliary equation is r squared plus 5r minus 6 equals 0. Now, if you do this a lot of times, you'll see that the thing is you're going to divide out the e to the power rt, and the y double prime will always lead to an r squared, the y prime will lead to an r, and the y will lead to a constant of 1. So if you want to, you can go straight from this to the auxiliary equation by just replacing your y prime by an r. You're going to replace your y prime, you're going to replace that by r squared, right? The second derivative becomes an r squared. The first derivative becomes an r to the power 1, which is just r. And the y, the 0th derivative, is r to the power 0. That's just a 1. So you see the y prime, r squared, or y double prime is r squared. 5 times y prime becomes 5 times r. Negative 6 times y becomes negative 6 times 1. Okay, this is something that will factor. And we're looking for a sum of 5 and a product of negative 6. So we can factor this as r minus 1 times r plus 6 equals 0. And so r minus 1 equals 0, or r plus 6 equals 0. That gives us r equals 1, or r equals negative 6. And now we're going to plug that back in. And so the two solutions that we obtain is, on the one hand, y1 of t equals e to the power 1 times t, or just t. And the other solution is y2 of t equals e to the power negative 6t. So those are two solutions to this differential equation. Now, we should note that the function that's identically equal to 0 is always a solution to this differential equation. And furthermore, when we have a pair of solutions, y1 and y2, like here, we can construct an infinite number of other solutions by forming linear combinations of these two. So The claim here is that y of t equals c1 times y1 of t plus c2 y2 of t is a solution for any value of c1 and c2, including c1 equals 0, c2 equals 0. And you can check that by substituting this into this equation and then rearranging it, and you will see that it will solve this differential equation. Now, the values of those constants c1 and c2 can be determined by imposing two initial conditions, as we will see in this example too. So we're going to solve the initial value problem y double prime plus y prime minus 2y equals 0 with initial conditions y at 0 equals 0 and y prime at 0 equals negative 1. So let's start out by finding the auxiliary equation. So I'm going to find the auxiliary equation, and I'm going to do the direct translation, right? So my y double prime, I replace that by r squared, the second derivative. Then the first derivative, that will be r to the power 1, or just r. And then minus 2 times y, this is there's no derivative, or the 0th derivative. So that just becomes a constant minus 2, and that equals 0. And then this factors as follows. We have to have a sum of plus 1, so we can do r minus 1 times r plus 2. That gives us a product of negative 2. And so we get r equals 1 or r equals negative 2. And again, that gives us two solutions, right? y1 of t is e to the power t, and y2 of t equals e to the power negative 2t. The general solution then is the following. Y of t is c1 times y1 of t plus c2 times y2 of t. Okay, now the way we find C1 and C2 is by using these initial conditions. Now note that one of the initial conditions uses the derivative of y. So let's find that derivative. So y prime of t is, well, let's first write this out, right? Y prime of t is c1 plus c2, and it's c1 times y1. We said that was e to the power t, and c2 e to the power negative 2t. And then y prime, if we take the derivative, that first term doesn't change. So that first term is still e to the power t with a c1 in front. And the second part, due to the chain rule, the negative 2 moves to the front. And so we get negative 2 times c2 e to the power negative 2t. So we have a c1 at the start. So that's the derivative. So here are our initial conditions. So we have Let's take a look at the first initial condition. Y of 0 equals 0. That leads to, for the first derivative, that leads to 0 equals, and then c1 e to the power 0 plus c2 e to the power negative 2 times 0. And when you simplify that, you get that 0 equals c1 plus c2. The other initial condition is that y prime of 0 equals negative 1. So that leads to negative 1 equals, and now let's plug in 0 here. We get c1 e to the power 0, and then minus 2 times c2 e to the power negative 2 times 0. And that simplifies to 0 equals c1 minus 2c2. So what we have here is a system of equations in two equations in two unknowns. And what we can do, oops, I see that this needs to be a negative 1. And what we can do is we can subtract the second equation from the first equation. So we take this, we subtract that from the first equation. That means 0 minus minus 1. That gives us a 1. C1 minus C1, that cancels. And then we have C2 minus minus 2C2. So that's 1 plus 1C1 plus 2C1. That gives us 3, or C2. 1C2 minus minus 2C2. That gives us 3C2. And so the conclusion there is that C2 equals 1 over 3. Then we go back to our equation here and we plug in what we know for C2. And from that, it follows that C1 equals negative 1 over 3. And then our final answer is that y of t equals C1 times e to the power t, so that's negative 1/3 e to the power t, and then plus c2, so that's plus 1/3 e to the power negative 2t. Now, in general, we can say that if we have distinct real roots for the auxiliary equation, and we denote those roots by R1 and R2, then y of t equals C1 e to the power R1t plus C2 e to the power R2t is the general solution to our differential equation.